Recall for a single variable function, being y, as a function of x, which was differentiable with respect to x, and x is also a differentiable function of t. Then that implies y is also a differentiable function of t, and by the chain rule, to obtain a derivative of y with respect to t, we differentiate with respect to x and multiply that by dx dt. So this is the chain rule for a function of one variable. And similarly, for a differentiable function z of two variables, where x and y are differentiable functions of t, then the composite function z is a function of x, which is a function of t, and also a function of y, which is also a function of t, is a differentiable function of t. And the derivative of z with respect to t can be obtained using the chain rule in a similar form to the single variable function. Except we take the partial derivative of z with respect to x and multiply this by dx dt, and add the partial derivative of z with respect to y and multiply by dy dt. So noting x and y are functions of one variable, so that's why we have the ordinary derivative for x and y. So here z is the dependent variable, and x and y are intermediate variables, and t is the independent variable. So note how these derivatives are evaluated. So this derivative is evaluated at a particular value for t. So for example, if t was t0, then the partial derivatives will be evaluated at a point with x coordinate at t0 and a y coordinate at t0. And dx dt and dy dt are evaluated at t0. Now let's look at an example being a hyperbolic paraboloid defined by z is equal to y squared minus 4x squared, and x is a function of t, and y is also a function of t. So what we're doing here is essentially mapping this curve, being a circle parametrized by t, which is shown here in the xy plane. So mapping the circle to this surface gives this curve that looks like a saddle. So substituting for x and y in z, we get the z coordinate, which is sine squared t minus 4 by cosine squared t. And if you apply your double angle trig identities, we get z is minus 3 on 2, minus 5 on 2, by cosine 2t. So for example, when t is equal to 0, x is equal to 1, and y is equal to 0, and z is equal to minus 3 on 2, minus 5 on 2, which is negative 4. And for example, for t is equal to pi on 2, x is equal to 0, and y is equal to 1, and we get cosine pi, which is negative 1, so that gives minus 3 plus 5 on 2, which gives z is equal to positive 1, as we can see. Now let's make a bit of room over here. So evaluating the derivative of z with respect to t, we get minus 5 sine 2t. And similarly, if we evaluate this derivative using the chain rule, So we take the partial of z with respect to x, which gives minus 8x, multiply by dx dt, which gives minus sine t, and plus dz dy, which is 2y, by dy dt, which is cosine t. And now we can substitute for x, so that gives 8 cosine t, sine t, and substituting for y, we get plus 2 sine t cosine t, so that gives 10 sine t cosine t. And using our trig identity, that's equal to 5 by sine 2t. So we got the same result by direct differentiation and using the chain rule. So the chain rule gives the rate of change of the elevation z as we travel along this curve mapped on the surface. Suppose we have a differential function of 3 variables, being x, y, and z, and x, y, and z are differentiable functions of the variable t. So we have y of t and z of t. Then the composite function w is a differentiable function of t. So we can write w is f of x of t, y of t, and z of t. And therefore, the rate of change of w with respect to t has a similar form to the derivative of a function of 2 variables, where we apply the chain rule. So we have the partial derivative of w, or f, with respect to x, by dx dt, plus the partial derivative of the function with respect to y, by dy dt, plus the partial derivative with respect to z, by dz dt. So if this derivative is evaluated at time t0, then our partial derivatives are evaluated at a point with coordinates x at t0, y at t0, and z at t0. And noting the ordinary derivatives are evaluated at t0, because x, y, and z are functions of t. So as an example, suppose w is z minus y squared plus 4x squared, and x is cosine t, y is sine t, and z is equal to t. So to find the derivative of w with respect to t, we take the partial with respect to x, which is 8x, by dx dt. So that will be minus sine t, plus the partial derivative of w with respect to y, so that will be minus 2y, multiply by dy dt, which is cosine t, and plus the partial derivative of the function with respect to z, so that will be 1, by dz dt, which is also 1. And substituting for x and y, we get minus 8 by cosine t, sine t, minus 2 by y, which is sine t, by cosine t, plus 1. So that gives 1 minus 10 by sine t, cosine t, which by the trig identity is 1 minus 5 sine 2t. We can extend the chain rule to differentiable functions of 3 variables, being x, y, and z, where x, y, and z are also differentiable functions of the variables u and v. So we have y of u and v and z of u and v. So we have the dependent variable w with x, y, and z being the intermediate variables, and u and v are the independent variables. So taking the partial derivative of w with respect to u, we get the partial of w or f with respect to x, but the partial of x with respect to u, and plus the partial of f with respect to y, but the partial of y with respect to u, and similarly the partial of f with respect to z, but the partial of z with respect to u. And the partial derivative of w with respect to v is obtained in a similar way. So we have the partial of f with respect to x, by the partial of x with respect to v, plus the partial of f with respect to y, by the partial of y with respect to v, and plus the partial of f with respect to z, by the partial of z with respect to v. Now as an example, suppose our function w, which gives a quantity distributed on a surface, so for example, the light intensity distributed on a sphere. So we have the light intensity increasing with respect to x, so w is a function of x. And suppose we define every point on a spherical surface using the angle theta and the angle phi in spherical coordinates, and the sphere has a unit radius of 1. So if we take the radius sine phi, then we get this distance over here, which is the length of the projected radius in the xy plane, and taking this value cosine theta gives the x coordinate of that point. And similarly, y is the unit radius sine phi, which gives the length of the projected radius in the xy plane, and taking sine theta gives the y coordinate. And z is the radius cosine phi. So essentially this sphere is parametrized using u is equal to phi and v is equal to theta. So theta is typically referred to as the longitude and phi is the latitude if we measure phi from the xy plane rather than a vertical axis. And now using the chain rule, we want to find the rate of change of w with respect to phi. So in this case, w only depends on x. So these partial derivatives drop out, and we have the ordinary derivative of f with respect to x, multiplied by the partial of x with respect to u. So the first derivative gives 1, and the partial of x with respect to u, being phi, is equal to cosine u cosine v. And similarly, the rate of change of w with respect to v is the derivative of w with respect to x. So again, noting that w is a function of one variable, multiplied by the partial of x with respect to v. And note that the partial of f with respect to y and with respect to z is 0 in this instance. And the partial of x with respect to v being theta will give minus sine phi, which is u, by sine v being theta. So when u is equal to pi on 4, for example, and v is also pi on 4, we get the location of this point on the sphere. And we expect the maximum light intensity, represented by the quantity w, to be at the maximum value of x on the sphere. Now let's make a bit of room. So if we evaluate these partial derivatives at pi on 4, so we have the partial of w with respect to u, where u and v are both pi on 4. So cosine pi on 4 is 1 on root 2 by cosine pi on 4 gives 1/2. And similarly, the partial of w with respect to v, evaluated for the same values of u and v, is minus sine pi on 4, which gives minus 1 on root 2 by sine pi on 4, so that gives minus 1/2. So along u or phi, the temperature is increasing. So note that the temperature increases with respect to x. So when we traverse the sphere from the top, we're going towards the maximum value of x. So the rate of change of w with respect to u, being the angle phi, is positive. Now if we traverse the sphere in the theta direction, we have the partial of w with respect to v, being theta, is negative. So we're moving away from the center of the sphere, where the light intensity is a maximum, to the edge of the sphere along theta, where the light intensity drops off. So it makes sense that this partial derivative is negative. Suppose we have a function of two variables, x and y, being a differentiable function, and this function is equal to 0. So it's implied that y is a function of x. Then at any point where the partial derivative of f with respect to y is not 0, we can obtain dy dx as the negative of the partial derivative of f with respect to x on the partial derivative of f with respect to y. So this can be shown using the chain rule. So if we take z is equal to f of x and y, and that's equal to 0, then that means the derivative of z with respect to x is also 0. And evaluating the derivative of this implicitly defined function with respect to x, we can use the chain rule. So we have the partial of f with respect to x by dx dx plus the partial with respect to y by dy dx. And this derivative evaluates to 1, being the derivative of x with respect to x. So we can get rid of this term, and then subtracting the partial of f with respect to x from both sides, and dividing by the partial of f with respect to y, we get this expression for dy dx. If we have a function of three variables, being x, y, and z, and in the implicit form, this implies that z is a differentiable function of x and y, then at any point x, y in the domain of the function, and where the partial derivative of f with respect to z is not equal to 0, then we can write the partial derivative of z with respect to x as minus the partial of f with respect to x on the partial of f with respect to z, and the partial of z with respect to y can be written as minus the partial of f with respect to y on the partial of f with respect to z. And this can be done using the chain rule. So for example, if we set w is equal to f of x, y, and z, where z is a function of x and y is equal to 0, then taking the partial derivative of w with respect to x, we can apply the chain rule. So we have the partial of f with respect to x by the partial of x with respect to x plus the partial of f with respect to y by the partial of y with respect to x, and plus the partial of f with respect to z by the partial of z with respect to x. And on the right hand side we have 0. Now the partial derivative of a function x with respect to x is 1, so we can get rid of this term. And by taking the partial of w with respect to x, we're treating y as a constant. So this derivative evaluates to 0. And then subtracting the partial of f with respect to x from both sides, and dividing through by the partial of f with respect to z, we get the partial derivative of z with respect to x. And similarly, the partial derivative of w with respect to y can be also obtained using the chain rule. So we have the partial of f with respect to x by the partial of x with respect to y plus the partial of f with respect to y by the partial of y with respect to y plus the partial of f with respect to z by the partial of z with respect to y. And on the right hand side we have 0. So again, by taking the partial derivative with respect to y, x is held constant. So this partial derivative is 0. And the partial derivative of a function y with respect to y is 1. So this derivative is 1. And subtracting the partial of f with respect to y from both sides, and dividing through by the partial of f with respect to z, gives this result. Evaluate the derivative of w with respect to t for the following function at t is equal to 0. So we see that w is a function of 3 variables, being x, y, and z, which are functions of t. So we can apply the chain rule and differentiate with respect to x and multiply by dx dt plus the partial derivative of f with respect to y by dy dt plus the partial with respect to z by dz dt. So the derivative of w with respect to x is minus e to the z by dx dt, which is minus 1 on the square root of 1 minus t squared, being the derivative of arc cosine. And then we have df dy, which is 1 on y, by dy dt, which is 3e to the 3t, plus dw dz, which is minus x e to the z, by dz dt, which is 1 on t plus 1. And now we can substitute for x, y, and z. And minus multiplied by minus is plus. So we have e to the z, which is e to the natural log of t plus 1, being t plus 1, over the square root of 1 minus t squared, plus 1 on y, being 1 over e to the 3t, by 3e to the 3t, which is 3. And minus x, being the arc cosine of t, multiplied by e to the z, which is t plus 1 on t plus 1, which is 1. And evaluating the derivative at t equals 0, we get 1 plus 3, and the arc cosine of 0 is pi on 2. So we get 4 minus pi on 2. Evaluate these partial derivatives for the following function w at the following values of u and v. So here we see w is a function of 3 variables, and x, y, and z, being the intermediate variables, are functions of u and v. So applying the chain rule, we have the partial of w with respect to u is the partial of w with respect to x, by the partial of x with respect to u, and plus the partial of w with respect to y, by the partial of y with respect to u, and plus the partial of w with respect to z, by the partial of z with respect to u. So the first derivative gives y plus z, and the partial of x with respect to u is 1, plus the partial of w with respect to y, so that gives x plus z, while the partial of y with respect to u, plus the partial of w with respect to z, which is y plus x, by the partial of z with respect to u. So we get u plus v plus uv plus u minus v plus uv plus y plus x, which gives 2u minus v plus v multiplied by v. So we see that the v's cancel, and we obtain 2u plus 4uv. And evaluating the partial derivative at u equals 2 and v equals a quarter, we get 2 by 2, which is 4, plus 4 by 2, which is 8, on 4 is 2. So that gives 6. And in a similar way, you can evaluate the partial of w with respect to v. So we just replace the u. So the partials of w with x, y, and z remain the same. And the partial of x with respect to v is minus 1. And the partial of y with respect to v is also 1. And the partial of z with respect to v gives u. And now let's get rid of this result. So this time we get minus y plus z, which is u plus v plus uv, and plus x plus z, which is u minus v plus uv and plus y plus x, which gives 2u multiplied by u. So this time we have minus u plus u and minus uv plus uv and minus v is minus 2v plus 2u squared. And therefore, evaluating the partial derivative for u equals 2 and v is 1/4, we get minus 2 by 1/4 being minus 1/2 plus 2 by 2 squared, which is 8 or 16 on 2, which gives 15 on 2. Evaluate the partial derivative of z with respect to y given the following function at the given point. So using implicit differentiation, the partial of z with respect to y is the negative of the partial derivative of the implicitly defined function with respect to y on the partial derivative with respect to z. So we have negative, and taking the partial of f with respect to y, we get minus sine of x plus y minus sine of y plus z. And the third term drops out, and taking the partial of f with respect to z, the first term drops out, and we get minus sine of y plus z minus sine of x plus z. And evaluating this partial derivative at the given point, having coordinates pi on 2 and pi, we have the negative of minus sine of pi plus pi on 2, which is 3 pi on 2, minus sine of pi on 2 plus pi, which is also 3 pi on 2. And in the denominator, we have minus sine of pi on 2 plus pi, which is also minus sine 3 pi on 2, and minus sine pi plus pi, which is minus sine of 2 pi. So what we get is negative of minus minus 1 minus minus 1 over minus minus 1 minus 0. So the derivative evaluates to minus 2 on 1 or negative 2.